Okay, some people asked me to put it online, and I totally forgot. All right, so for this one, we see we have 4 torques here. Okay, right away, notice 1. Guys, come on, we have enough time to settle. 1, 2, 3, 4. Now, notice 2 of them were at 90 degrees. There's your 90 degree right there. There's your 90 degree right there. So for those, what is the sign of 90 going to be?
1.
Good. Is this going to be a positive torque or a negative torque?
Positive.
Good. How about this one?
Negative.
Because it's going to spin it this way. Be careful, you're really pushing up, and the dots or the fulcrum is right here. This one? Positive. And then negative. Right? Again, pushing up on the right side gets it to spin counterclockwise.
I did it wrong.
So for each of these,
Are you recording that?
yes, for each of these, think about.
Switch your science software.
Should I not go over this? Because we're all talking. Are we good?
No, go over it.
Then stop talking. Or I'm not going over it. Pick one or the other. Are we going to stop talking and go over it? Let's do it then. Because it seems like nobody cares. So if you don't care, I'm not going to go through it. This is 50 newtons at a distance of 10 meters. So what's the torque? Positive 500. Over here, we're going to have 30 degrees. Sine of 30 is 1/2. So I'm going to have half of this number times 15.
Isn't 187.5?
And I'm going to make that negative. Up here, I'm going to have 12 as my force over a distance of 20. Again, 20. 12 times 20 is?
240.
Thank you. 24, 240.
Come on, Christian. Come on, Doc.
Again, guys, force is 12. The angle is 90, so we just multiply by the lever arm, which is 20. The final lever arm is 30. The force is 10, and we're 15, 5, and 10 is 30. The final one? The final lever arm is 30. Check your math here. Now, for the 10 lever arm. Star, what is it? What is the lever arm? Thank you. So here, this is 10 as a force. We're doing the force times the distance. Now here was the tricky one, and I went over. We got to use the 60 here. Okay, 0.866. What do you get for that, Julian?
I got 86.6 and
You didn't multiply by the 30.
Yeah.
86.6 would be multiplying by 100.
Yeah, I didn't.
It's not 86.6. 300 times 0.866.
this is the force. This is the force of 10, and the thingy is 60.
Guys, this distance from here, the fulcrum, to the point where the force is applied is 30.
That's what. Oh, okay.
That's a 30 distance. Remember, you're going 15, another 5, another 10. Okay, 259.8, thank you. And that's going to be negative. Now, take the positive and the positive, add them up. You're going to get 740 positive, and then subtract the sum of the other two. What's the sum of these two going to
Well,
be?
you gotta add them up, please.
Yeah, it's going to be a 3, carry the 1, 7, carry the 1, 4, carry the 1, 4. Okay? So subtract these two numbers. So what are you going to get as an answer? What kind of an answer? Positive. A decimal, yes. Decimal for sure. But for torque purposes, positive. Positive means clockwise. Our final answer will be a clockwise.
I had it in my head. And then he got in the way when he went like
I did everything right.
Guys, let's listen to Houston, please.
I did everything right. Like, this is why I stopped doing homework. Because I do everything right and
Okay.
get totally different numbers.
Check your degree mode. Are you in degree or reading?
I didn't even use the calculator.
And how'd you get different numbers?
Well,
Did you?
I used the calculator for the last one.
Okay, fair enough. I don't know how you got different numbers.
For the first one, I got 100. For the second one, I got the 240. For the third one, I got the negative 187.5.
So you got these ones right. Good.
Yeah.
Why is this 100? It's 50 times 10.
I got that one right. That's the third one.
Can you give us another problem like this?
Dude, you said the first one I got 100, then you said the second one I got 240, then you said the third one I got 187.5.
Right. So I got something in the last one.
Check your math, look at your work.
I got the last two.
That's why it helps to show work there. I mean, go back and look.
He probably plugged in right into 3 over 2.
I don't know. Again, Houston, I can't tell you what you do wrong unless I see your work. So until you show your work, I can't help you there. Show me after class, that's fine, dude, absolutely. Again, please, notice, guys, this is .866 because we're using 60. Sure use 60 there.
Can we get another problem like this?
We're going to start another one today like this, yeah?
Mr. I have a calculator to borrow for this
For
class.
this one? Yes, 15.
Negative 25 times
Times sine of 30. That's 30.
that one is up there, and that was down. This 30 over here.
Star, it's always the angle between the x-axis and the arm. And the x-axis and the arm, doesn't matter which one. Remember, reference angle I said.
So I thought it 30.
This is because 30 is with the y, okay? Again, if you're giving it here, leave it alone. What's that?
Do you have a calculator I can borrow for this class?
A calculator?
Yeah, my battery's dying.
I don't even have my own calculator. I really don't. I gave it away to my little brother. I used it. I did. I used the one I have on the computer. You guys see the one I have? I opened that up and used it. Do I need to buy one? All right. Or just clever could be a nice word.
Is the TA-84
I thought we did those.
program free?
Something new, don't worry. No. Mr. Smith bought it. He got 2 licenses. He gave me one of them. Well, he might have more than 2, but I know he had enough to give me
Where is
one.
it at?
My phone?
Calculator.
The black one?
I'm sure.
Locker
He
probably?
can get
I don't know.
Which one?
Same, just saying.
What if we had a quiz so we would have failed?
I know we would have failed, but I would have thought that analytically.
Well, I don't know where to go.
All right, please.
Do you want? Oh my god.
Google YouTube converter.
Video, hey, video, number 2, MP3. .net.
That's that blue one? I found a better one.
Which one do you?
I don't know the name of it. I have it saved as a favorite.
My friend gave me another one too. I don't know, maybe it might be that one.
I'm gonna add it on my section.
My Facebook game is really
Yeah, it really is unique.
Please write while you talk. Please write while you talk. Let's go.
I don't even want to do this. I don't have a calculator.
Do we have our numbers or just one? I don't know if we do this.
We're doing a lot here. It's going to be a tough problem. I'm going to explain it though. We do everything with variables first. And we're also going to look at our forces and forces.
What is that?
Sorry, this is beta, and theta. And that's just 90 degrees.
Put 60 right there.
Yeah, it's another angle. That's all it is.
Who the heck X that?
I don't know. I didn't use alpha for my. We only been using. I'm making comments.
Learn nothing in algebra.
No, it's okay. Thank you, though. No,
Never had that.
it'll heal. All right.
No.
Now,
Not necessarily.
Yeah, if there's 2 thetas there. Yes.
No, when you got that.
Like if you have.
That's like if you have X and X.
Still, what you guys like sign data, always tell the difference.
If you're gonna use three variables for angles, it's beta, alpha, and theta. You're never gonna use the same symbol.
If instead of beta, it was theta, that means.
Theta 2, we call it.
Oh, then just theta 2.
If it was just theta, they would be equivalent, automatically.
Okay. I know
If one was theta 1 and one was theta 2, then they're different. If these were all just called F's, then they were all the same force. Alright, so here's what we're going to do now. What I really want to do today is look at what's called like full body equilibrium or rigid body equilibrium. Again, not a topic you're going to learn even in physics AP. This is more of an engineering thing, but it's what we're actually using for torque. This is where torque is used. So, if we look at this beam, or in this case we can say it's a rod or a beam, and we see that there's a pivot point here. Okay, there's our pivot point. So we're going to have a force pushing down, and then a force pushing back up, and another force pushing up. And what we want to look at in this problem is to say to ourselves, when will this bar or this rigid body be in equilibrium? When will it be balanced? When will it not be moving? And we want to try to figure out what the conditions are needed. Now, well, the hard part, or not hard part, but the part you have to remember is, torque is also what we're looking at, but we have to have also force equilibrium. So if you remember, if I was pushing a box across the floor, and my force and the force of friction were equivalent, then F net would be 0. So it would have been moving at like a constant velocity. We talked about that. So here, what we need to look at are three major conditions. The first one, we have to look at all of our torques and show that they are equal to each other. Second, we have to look at our forces in the y direction, show that they are equal. And third, the force is in the x direction. There is no force in the z direction out of the board here. We're applying a force up and down only. That creates a force, because they're at angles, that creates a force up and down, and it's going to create a pull on it. Again, if you took a rod like this and you pushed in this angle, it's going to create a pull, and it's going to pull the shaft this way. So it's going to be pulling apart. So you're going to have like tension here. So this is going to be compressing on this side. That's going to be pulling down on that side. Okay?
So that to be equal torque in y direction.
And x direction force. Again, equilibrium of torque, and we'll write this in a second. Force equilibrium in the y, force equilibrium in the x. Okay? We need those three things. The object's not going to move, that's what we're saying. We want it to be in equilibrium. So what do these values have to be for it to be stable, so that it's not moving? This is done all the time in statics. For example, right now, we're standing on the floor. There are cross beams that go across here. Okay, they provide a support. Now, me standing here, Isael sitting there is providing a force on that beam, just like this right here. This is like Isael sitting maybe at an angle, he's leaning. So his force might be pushed to the side a little bit. And then I'm standing straight here. That's what you're thinking about. So we're putting forces on this object, and it's not moving. It's not bending. Okay, so we're trying to figure out, why isn't it moving? Why isn't it bending? What are the conditions that are needed? It needs to be in torque equilibrium, in force equilibrium, in the y, and in the x. Okay? The minute you go on to look at, if you go and take statics, and you go and take dynamics, you're going to see that you have a z direction also, and that's going to create 9 equations instead of 3. So it gets a lot more complex. We're just going to simply look at 3 now. So what we're saying is this. Torque net needs to be 0 so that there's no torque on it, so it's not moving. And then F net in the y equals 0, and F net in the x has to equal 0. Most likely yes, because it's super close compared to these two. But these are variables, aren't they? So we don't really know. If you look at it as drawn to scale, absolutely. Okay? But keep in mind, Isael, that this going up and this coming down are providing the same torque. They're both turning it this way. But this one's going back, and it's at 90, so it's stronger. Okay, for this problem, here's what we'd like to do. First, Isael made a really good point now. If we're looking realistically at numbers, this F3 is providing a torque in the clockwise direction, right? This way, and it's providing at a 90-degree angle, and it's really furthest from the fulcrum. Julian, this way, please. Here, this one is providing a negative torque. This one is providing a negative torque. And those happen to be closer in, and they're not at 90 degrees. So they're going to be of less value. So there's a good chance that if you were finding numerical answers, F3, okay, F3 would be probably larger than the sum of these two also. But what we're trying to do is say, what if they're equivalent? What will cause this not to rotate? So what we want to do is this. We want to come up with our equations in every direction. We'll start with torque, because we're using torque recently. So if you were to do torque net, and just think logically, forget about numbers for a second. If you were doing torque net, you would say that it was F3 times the distance times the sine of 90. Again, think back to last night's homework. F3 would be a number times the lever arm, which is really D3 plus D2, the combination of them, that's the distance, times the sine of 90. So for this problem, that's all you want to write. F3, parentheses, D3 plus D2 times the sine of 90. Now, don't even put the sine of 90. How come? Because it's 1. Okay, and that's why there's no angle there. Remember, our standard formula for torque is going to be equal to F times R times sine theta. Byron.
You know how you said that we had D3 plus D2?
Yes?
In the problem before, you know how we had...
We had numbers there, yes. We added them.
I know that, but like we had the 15 and the 5. How come we didn't add those for the second one?
We absolutely...
For this one. Because it was 15 meters and 187.
Well, there must have been 50 meters in the end then. It's how far it is, Byron. You're looking at the wrong one then. The second one was only 15 away. The third one was 20 away. The fourth one was 30 away. Okay, they were all different distances.
Doesn't torque take care of like that direction?
No, it does not. Because you have a stress on it. This is providing a stress in that direction. This is providing a stress in compression. So you have to account for those two. Okay? Torque only takes into account the torque on the shaft itself. This is talking about annual stress, or axial in a sense too. You can think of this as the axis across the whole way, and there's stress on it being pulled apart. That's only the first one. Again, this causes it to go this way, which is positive, so I leave it as positive. Now, looking at F2 next, it's going to be what? Negative right away. Good. How far away is F2 from the fulcrum? D2. Take a look here. F2, here's its intersection point. The distance away is D2.
So the fulcrum is the dot?
The fulcrum is always the dot, the same as it was before. Okay, just like last night. The fulcrum is the pin. The pin. Okay? We call it a pin joint. Yes?
My question is, like, say for instance on the test, when you give us a diagram like that, are you gonna point out like going from like a certain point?
You're going to see the diagram exactly the way you saw at the beginning of the problem. You're going to have a pin on there, you're going to have your forces, you'll have your angles measured, all that stuff.
Okay.
I'm not going to say this is the pin, this is the fulcrum. No. You'll get a diagram and you might say, for example, for a test problem you can think about, you'll get a diagram like this and say, write the 3 equations needed for equilibrium. And that's what we're doing right now. This is the first equation. We're going to get to F net Y and F net X in a minute. Kenny?
That theta that you just put there, do you use that theta or you use the opposite of it? What I mean, it's like
Remember, you always use the theta, that's the angle between the force line and the x-axis. That's this theta. So you're using that theta.
Okay.
If the theta had been given up here, Kenny, if theta had been given up here, then you'd have to use 90 minus that.
Okay.
Okay? Again, if it had been given, instead of beta over here, you'd have to use 90 minus theta. Okay? Because you want to use that angle. Always this angle here, or always this angle here.
Okay.
Think about reference angles, people. If this was your terminal side, that would be a reference angle.
Yeah.
If this was your terminal side, that would be a reference angle to the nearest x-axis.
Yeah.
So,
Reference angles are huge in engineering, just so you know.
alright, so I have a question. So we always just gonna think about it as if it's 90 degrees. So like the theta's on the other side, we're just gonna not assume it's 180 inside of 90.
Now, if the theta is given here,
Right.
Houston, you have to use 90 minus that value.
But why is it like 90 minus? Why isn't it just?
Because watch, if this was 30, Houston, if that was 30, what would this angle be then? Yes, you do. 60. It's 90 degrees. 60 plus 30 is 90. So you use 90 minus whatever this angle is.
Alright, but that's not what I'm saying. Like, say that dash line isn't there, right?
It is there, though. It's not there. It's always there.
But I'm talking, okay, that's what
It's a perpendicular.
It's always there.
You always have a perpendicular y-axis. You can draw a dashed line there. You can draw a dashed line here. You could draw a dashed line here. There's always dashed lines, right? They're just reference points. So this happens to be right there. It's 90 degrees. This happens to be less than 90 degrees. If you had been given, no, this as your theta, don't write this, please. If this had been theta, how do you get this value? You do 90 minus that value to get 60, right? So this would be 90 minus theta. So if you had been given this as theta, in your formula, you'd have to use sine of, parentheses, 90 minus theta. Okay, you're always using the complement if you're given the y-axis. Okay, if you're given to the nearest y-axis, like this 30, you would use the complement of that. Okay, so closest to the x-axis, if you want to remember. Just think about reference angles, people.
That's why last night you chose 60.
That's exactly right, because it was given as 30 down here last night, and I said use 60, because 90 minus 30 is 60. You know what? If you want to do that, let's make this just so we can all see that exact thing. Take your beta in your diagram, guys. Put beta here instead, and we'll just show that. So we're not unclear about this at all. Let's do that to clear up anything. So put beta over here instead, please. And again, we need to use this angle here, given by that curved black line right there, which is not beta, but how much? 90 minus beta, because if beta was 30, you would do 90 minus 30 and get 60. If beta was 45, you would do 90 minus 45 and get 45. So this angle here is really 90 minus beta. So if you're given a diagram where beta is right here, you have to start automatically by writing this in here. Because in the last course we're about to write right now, we're going to use 90 minus beta.
Yeah.
Okay?
Would it be the same thing for theta too? Or no?
Would it be what?
Same thing for theta?
In this diagram?
Not in this diagram, but...
Sure.
Okay.
Sorry, let me just clear this up. Beta and theta are the same thing. They're just angles. They're just different angles. So beta, gamma, delta, you can use any symbol for angles, really. I'm just using the standard ones. They're alpha, which looks like a fish. Okay, you remember that from law of sines? Last year we used that. We used alpha, beta, and theta last year in algebra 2. Okay, so here, 90 minus theta.
So these sororities are a bunch of angles.
What? Which way does this cause it to turn? Counterclockwise, so it's negative. F1, the distance. Ken, turn around, please. Come on. The distance between the pin and the force is D1. So it's F1 D1 sine of 90 minus beta. 90 minus beta is in parentheses.
Can I just put 90 minus beta on?
90 minus beta needs to be in parentheses.
I can't put sin.
90 minus beta needs to be in parentheses. Because this is your argument.
Parentheses.
Okay, you're taking the sign. Elizabeth, listen. If you had written it without the parentheses here, if you put the parentheses around the whole thing, it would be read as sine of 90, which is a number, and then minus beta. But you're doing sine of quantity 90 minus beta.
It comes with some
Okay?
This is so far.
Again, 90 minus beta.
If it comes with some random number, the answer is going to be so good.
No, there are no numbers. This is all variables, guys. All variables. Now, take a look. In the beginning, we said for equilibrium, torque net needs to be 0. So your first equation is really with a 0 over here. So go ahead and put a 0 there. That's equation 1. That is our torque equilibrium equation. Again, if you want to write your notes here, for your own notes, this is torque equilibrium. We're just finding an equation that makes this bar at rest. It keeps it at rest. Now, in physics, guys, and in statics, what you're going to do later is this. If you're given, for example, if you're given a force, and you're given all the distances, maybe you're solving for theta and beta. Or maybe if you're given the angles and the distances, you're going to be solving for your 3 forces. Because there's 3 forces, right? And how many equations are we going to have? 1, 2, 3. Again, however many variables you have, you're going to solve for that many. It's all right. You're going to solve in that many equations. Now, 3 equations means, at most, we can have 3 unknowns. So for this problem, if you were given, ready? If you were given the angles, and if you were given all the D's, you would be left with F3 unknown, F2 unknown, F1 unknown. And that's like having X, Y, and Z variables. You can use a matrix to solve this. This is like some number times X, some number times Y, some number times Z. And if you have 3 equations and 3 unknowns, you can simply use a matrix. Okay, so what I really want to do then is later use numbers, and we'll explain that. But I'm trying to show you where they come from. So that's the first equation.
Are we doing, is that what we're doing?
You have to do something like this in the test, absolutely. Today, if there's 5 courses, then you have 5 parts. It's always depending on the setup. If the setup is different, They're different equations. I can give you these three and tell you that, sure. But you have to come up with this. It's based on the problem. I can't give you that. If this setup had been different, equation's totally different.
I don't remember half the stuff I did.
Second one. Guys, come on.
We changed the test to Thursday, right, Mr. Al?
Oh,
Next, let's do the force equilibrium in the y direction. And this is so much easier, guys. The force ones are very easy, because we're just doing exactly what we used to do. So remember, if you want the y component of some force, you need to look at what angle, or the blank of the angle. The sine or the cosine?
Sine, cosine.
For the y direction, guys.
Sine.
Y is sine.
90 minus this?
Y is sine. So here, let's take a look. F3, which way does it act? Straight up, doesn't it?
Yeah.
So there's no angle there, we don't have to worry about it. If we did sine of 90, it would just be 1. So F3 acts in the positive y direction. Again, so here we're going to put 0, thank you, equals F3 to start. Positive, because it's acting straight up. Next, F2, don't even look at the angle yet, just answer this question. Does it act mainly down or mainly up?
mainly up.
Down.
Mainly down. Again, F2, look at the angle. It's acting down and to the left. Again, it's a vector. It's acting down like that and to the left like that. That's how we think of this. So this is going to be a negative F2. Now, I want to know I want to know the y component. The y component is always sine of your angle.
Oh, never mind.
So in this case, let's go back to our angle. It was theta. So the sine of theta. Again, if you want the y component of a force, you got to take the force itself and multiply by the sine of the angle. The angle here is theta. Next, the last one. It acts up or down? Up. And it has an angle of 90 minus beta. Remember, this angle is done with. That angle is gone. Once we rewrote 90 minus beta, just ignore it, please. So it's 90 minus beta, so it's going to be acting upward, F3, at an angle of 90 minus beta.
That's F1.
F1, thank you, Bridget. I did it 1, 2, and 3 instead of 3, 2, 1. And that's not a theta, that's a 90.
For the F3, there was a sine of 90, right?
There was a sine of 90 here. Remember, the angle is 90, but sine of 90 is 1. Okay, again, there is a sine of 90 there. Again, this acts upward, this acts downward, this acts upward. This acts at an angle of theta. This angle was 90 minus beta. Now, that's the y direction. In the x, what is the only difference going to be?
Cos.
Like, for instance, F3 goes, once it goes up, it also goes to the right, so would it be positive?
Be careful, it's not moving, remember? Equilibrium. So the first one, F3, is only acting the y. So if you do this one, it would be F3 times the cosine of 90. But what's the cosine of 90? 0. So this has no effect on the x direction, which is obvious, because it's pointing straight up. This is not pointing at an angle, it's pointing straight up. So it's only in the y direction. So when we do the x equilibrium, we're only going to use these two forces, because this acts all in the y direction. And the way to prove that is because we're always going to use cosine of the angle. For the x direction, you use cosine. So you're going to do cosine of 90, but cosine of 90 is 0. So this has no effect on the x direction. Okay? So in the x direction now, let's do this. Okay, force equilibrium in the x direction. We have 0 equals, again, it would normally be F3 times the cosine of 90, but this just goes to 0. So you can just put a 0 in its spot, or you don't need it at all. Everybody see that again? It's F3 times the cosine of the angle. Well, the angle is 90. This is going to be what here? Which way is it pulling it? Is it pulling it to the left or to the right?
Negative.
To the left, so it's negative in the x. Now remember, now we're in the x. Look at this vector here. It's drawn to the left. So minus F2 cos of theta. Okay? These are both minus, in this case, because this one acts down, and this one acts to the left. This one is positive because it acts up. This one is 0 because it doesn't act in any direction left or right here. That's why this is 0. Last one, and here's where it gets tricky. This one acts which way? Left or right? Left. Look at this, and look at the normal, and then go this way. It's left. So this vector is to the left, and this vector is up. It was up a minute ago. That's where the positive came into play right here, because it was acting upward in the y direction. In the x direction, it's acting to the left, so it's going to be negative. And we're going to use cosine. So minus f1 cos 90 minus theta. Beta. Yeah, it's a beta, the last one, not a theta. Okay, again, the reason this is acting with negative is because it's really pulling it to the left. So take a look. For this kind of a problem, aren't these both acting to the left?
Yeah.
So there's going to be no way to have equilibrium on this unless when you solve for f1, you're solving for f1 is going to be a negative answer, so that it's going to be a negative, which really means, which is crazy to think about, which really means that it's not actually pushing that way, but it's pulling that way. So that's the weird part. But again, don't worry about that now. What I want you to see is this. You have 3 equations.
I have a feeling we're going to be substituting.
You have 3 equations. We can't see them all at the same time. Sorry. Can I zoom out a little bit?
Should be able to.
There we go. Okay? We've got our first equation, our second equation, and our third equation. Now, in this kind of a problem, here's what you're going to be asked. Again, you're going to be asked to find the forces if you're given everything else. So now if I gave you all the thetas, the betas, the D1, D2, and D3, if I gave you all those values, the only thing that would be unknown would be what I'm circling right now. This is the only unknown in the entire problem. This is 0 again, so it's gone. So you notice you have F1 is unknown in all 3, F2 is unknown in all 3, and F3 is unknown. With this kind of a setup, if you were to be able to determine this number, so say D2 plus D3 together was 20, and this was...
Ms. Schuster, please call the front office.
If this was somehow a 30, and this was like a 16, you now have a matrix. 20x plus 30 or minus 30y minus 16z, and you can write this all on a matrix and solve for your missing variables.
And if you can't?
Okay? You always can. You always can. Even here, the only thing is your answer you get will be negative. Oh, if you have a calculator, then you got to worry about it. Do it by hand. You can solve a system by hand. We did it last year. Houston, you have a question?
I was going to ask how come F1 was negative. Let's go to that.
Yes. In the x direction? Yes. F1 is acting to the left. That's why it's negative. So here's what I might ask you in the test. Just to give you a heads up. One of 2 things. First thing I might ask you to do is just simply set up the equations and give you all variables, like this. The other type of question, which we're going to do now, would be a question where I gave you the actual angles and gave you the distances and said find the 3 forces. And that's where a matrix would involve. So we're going to spend the next about 20 minutes solving another one of these problems with numbers involved. Okay, with numbers involved.
Can you do the matrix thing with your calculator up there too? I forgot how to do that.
As long as we get time to do it, guys, absolutely. Let's start.
May I go drink a water, Mr. House? May I go drink a water, Mr.
What view was I at before that? I don't know. Let's see if it extends. Does that work? No, it gets smaller. I don't want that. There we go. All right. Now, before we start, let's make sure we all understand here. One thing. How many equations do we have a minute ago? 3. So if I ever give you a problem with 4 variables or 4 forces, can you do it? Yeah.
No.
You only have 3 equations. Remember, there's only 3 equations. So if you have 4 forces, then it's not solvable. You need to be given one of the 4 at least. So I could give you a setup with 4 different forces, but give you one of the values, and then you could solve for the other 3. But you can only have 3 unknown variables. So I could also just do this. Remember in the last problem there was D1, D2, and D3? I could give you all the forces and all the angles and say solve for D1, D2, and D3. It's the exact same thing. Again, as long as you're only looking for 3 variables, you can always do this. Your angles are never going to be given unknown right now, because that involves a lot more work. You can't do that by solving with a matrix. You got to solve those equations simultaneously using a 3-dimensional graph. Okay? It's a lot more complex. So let's put our pivot point right here. Okay? Let's put our pivot point there. Let's put a force acting at 90 degrees in this direction. We'll call that F1. We'll say that this is 90 degrees, and we'll say that this distance is 5 meters. So again, the only thing now that's known is your force 1, force 2, force 3. The next one.
7.
Let's say we're given an angle like this. Okay? Now, I'm going to give you, this angle is 135 right here. Okay?
45.
We're told that this is F2, and we're told that the distance here is 7. I'll just say 7 instead of 7.5.
7.
Next.
7 meters, right?
Thank you.
What? 7.
Okay. So we got a force acting down on F3 over here at an angle with respect to the y-axis of 30 at a distance of how much? The total distance from F3 to the fulcrum? 17, very good. We've got a second one here. Okay, we've got a second one acting at an angle of 135 to the x-axis. F2 at 7 meters. And finally 90 degrees F1 at 5 meters. Christian.
It's not relative to the 10 meters. Like 10 meters.
30 degrees is the angle with respect to the y-axis that I drew here. That's that dashed line, and the angle and the vector itself.
Wouldn't it be 60?
What did it look like? Sorry. Oh, I see. I see what you're saying. Okay, I apologize. I'll move the 10 meters so it doesn't make that. I didn't realize that could have been misconceived that way. Yeah, this is 30, like this. Put the 10 meters down here. Put the 10 meters down there if it helps. Yep. I got you, Christian. So, for this kind of a problem, notice right away, you're going to have to make some angle changes. Okay? Byron, what do we got here, Byron? Good. This is 60 automatically.
What's the second one? What's the second one? What's the second
So ignore the 30, right?
35.
Ignore the 30. Excuse me.
Solving for the exponent in the right direction.
Uh-huh.
When you say sine of theta, are you talking about in respect to the x?
Absolutely. So in this case, that's why we changed to 60. Again, if you're given 30 here, don't use 30, write down the 60. Now, a lot of you are saying this isn't right, we're going to use what? 45, because 45 is left. But it actually doesn't matter, because the sine of 135, remember, from trig, ASTC, sine is positive, sine of 45 is positive, sine of 135 is also positive. Sine of 45 is root 2 over 2. Sine of 135 is root 2 over 2. So for this one, it doesn't actually matter. Come on, if you're going to do that, you can't lose focus. Come on. This is 45 here, really. Yes. Two of you guys. I know you want to share, but please focus. So here, this is 135. You can write 45 and use that, but you don't need to for this one. Again, the only reason being is because sine of 135 and 45 are the same. They're the exact same thing. Okay, but just to be safe, if you want to use the nearest, that's fine to change that. Over here, you do have to change it. So if you want to just be safe across the board, always use the angle nearest to the x-axis.
So,
okay?
So it doesn't matter.
For this one, it doesn't matter.
That's what I was trying to ask earlier, so it doesn't matter.
It does matter up here. It does matter up here. It doesn't matter here.
Okay. So right there for 60, you can't say it's 120. It has to be 60.
Sure, you could say 120. That's fine, Houston. Absolutely. Absolutely. Yep. So you want to use the supplement there?
No, you go with your
I know, but I'm just saying, if you want to in your head, it's absolutely fine. Yep. Okay, let's go through our equations.
That was, I don't want to use it.
It doesn't matter. It doesn't matter. Sorry, you gotta stop. It doesn't matter. 135 or 45, either one. You don't have to subtract. That's what he just asked too. Guys, you gotta stop thinking about what's right or what's wrong in one way. There's more than one right way to do these. Sine of 135 and sine of 45 are identical, so it doesn't matter there. Okay? I know math, you're always told there's one answer. There's not always one answer. And you're realizing this stuff now.
Right? I just had a conversation yesterday about this.
Okay, torque. Look at the first one here. Look at F1. F1. How far away is it from the pin? 5 meters. So we've got F1 times 5 times the sine of 90. Sine of 90 is 1, so I'm not going to put it. Again, this is really sine of 90 here. This is acting in which direction?
Negative.
Negative, or counterclockwise. So apply a negative sign on the front, please. Again, this is acting counterclockwise. Next, F2. It acts clockwise. Take a look this way, so it's positive. F2. What is its distance?
7.
Times the sine of?
45.
Good. Or 135. Either one. Remember, if you have something minus a value, you have to parentheses. Here you don't know. Okay? Last one acts in which direction?
Negative.
I heard both, guys.
Negative.
Negative because it's going which way?
Counter.
Counter. Okay? Here we have F3.
I said positive.
How far is the distance?
17.
17. Remember, guys, this is the distance here between the pin and the force. Times?
60. Sine of
Thank you. Times the sine of 60. That's our first equation. Take a look. How many unknowns do we have? 3. 3 unknowns. Next equation. I'm going to then go to Fy. Looking at our diagram, F1 acts in which direction, up or down? So it's a positive in the y. F1 acts straight up. So normally we would put sine of theta, but theta is 90, so it gets 1. Next, that's F1. F2 acts up or down? F2 also acts up. Take a look, it's pushing upward. So plus F2 sine of 45. Again, there would really be a sine of 90 here for the y direction for F1, but it's 90 is 1. F3 acts down. So minus F3 sine 60. Now, when you go to the x direction, it's no more difficult than what we just did. In the x direction, does F1 act in the x direction at all?
No.
It only acts up.
Why?
Okay? So we don't care about F1 in the x direction, because it would be the cosine of 90 again. But here, which way does this act? To the right or to the left?
To the right.
To the right. Again, take a look. Here's your angle. It's acting to the right. So it's positive F2 cosine of 45. So F2 cosine 45.
Minus.
And this one, I made sure to write in this direction, acts to the left. Again, F3 acts to the left. So it's minus F3 cosine 60.
Yeah, so basically, it's the same thing as the other one.
It is. That's exactly what I'm telling you. That's exactly what I'm telling you.
They're not cool because they're outside my life.
For each of these guys, you're going to use your generic equation to solve, really, and then you just plug in D1, D2, D3, theta, beta, gamma, delta, whatever you want to call it. Let's go ahead and take a look at our matrix now, what this would look like.
Everything's starting to go back. I just do everything.
When we solve a matrix, remember, all of your constants are on the right side. So see those zeros there? They should all be over here in your last column. And remember, this will be your F1 column, this will be your F2 column, this will be your F3 column right there. Okay, we did this in Algebra 2. And I think you've actually started doing it in pre-calc now
We did it
when you're
already.
solving quadratics for A, B, and C.
That's all my sure.
So F1 has a coefficient of what here? What's the coefficient?
-5.
-5, very good. Negative, because there's negative here, very good. -5. What's the coefficient here now?
7 times radical.
7 sine 45, thank you.
You put that in there?
Sure you can. Sine of 45 is a number. You can type it right into the matrix. It'll do it for you. Don't do the work on your own. When you plug in your matrix, type it like that. Over here, what do you get?
-17.
Negative, good James, -17.
Yeah.
Sine 60. That's my first row. Second row, what's my coefficient of F1? 1, not 0, make sure 1. Here it's sine 45. Here it's negative sine 60. Be careful, people. Negative. Notice all your negatives. Here, 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 and here. Those are the 4 negative circles. Now, the sine of 60 is radical 3 over 2. So if you want to write here root 3 over 2 and write root 2 over 2, that's also fine. If you want to write in all the roots. Because later, we're going to do cosine of 60, which is 1/2. So down here for negative F3, I'm going to put negative 0.5 there. Because I know that decimal. Okay, again, everybody see this is really cosine 60?
Yeah.
But cosine 60 happens to be an exact decimal. If I did that for this, it'd be 7071, ... This would be 866, ... all those other decimals. So I'm not going to put those there. But this is exactly 1/2. That's why I'm doing it. But in case you're wondering again, this is the cosine 60, which becomes the 1/2. The F2 is cosine 45. I can't write that value because I don't know it. And what goes here? 0. It's missing, guys. There's no F1.
So, Mr. Howard,
There was a 1 here, but there was nothing there.
what's up with those 7 zeros?
Those are all your constants, remember? You have to have them on this side, don't you, for the RF?
I don't know.
Houston, of course you know, we did this.
No, we didn't do matrix.
We did it in the summer, absolutely. Houston, we studied it, I'm 100% sure. It's 2 years ago, I know you gotta think back.
I don't even remember. Edgar doesn't even remember.
You guys gotta think back. I know for a fact, it's in the curriculum. I made the curriculum during the summer.
It's in the curriculum.
So, when we solve a matrix here, we take this matrix and plug it in. Okay, we're gonna plug this into our calculator. If you really don't remember at this point, watch what I'm about to do with the calculator. Go into it. Okay, open up your calculator, turn it on.
This is cool because
I found it. Would it be 3 times 4? That's all I want to know.
What?
3 by 4.
Column is zeros.
3 by 4.
The second.
Oh, is it 'cause
All right, let's take a look. This matrix has 3 rows and 4 columns.
It's 3 by 4?
So it's a 3 by 4 matrix. Those are the dimensions of the matrix. Again, 3 rows. This is not a row up here. This is just my headings. It's not a row. 3 rows, 4 columns. So, if you had me last year in Algebra 2, we talked a lot about examples where people bought food. And I remember Camille did the example where Camille went to McDonald's and bought 7 burgers, 3 fries, and 2 sodas. Bridget bought this, somebody else bought this. Find the cost of a burger, a soda, and a fry.
I remember that.
Okay? That's what we're doing right now, guys. That's it. Okay? It is. F1 is your burger, F2 is your fry, F3 is your soda. Okay? If you had me in the summer, we did this with only variables. If you had Mr. Smith for pre-calc, this year, he's already started doing this with quadratics. If you had Mr. Smith last year for pre-calc, which is you guys, you should have also used matrices to solve. Okay? So we're going to simply plug this in. So I go to my calculator, I press second, and then I hit matrix.
X to the
Okay? Mine happens to say 3 by 4. Ignore whatever it says. Don't worry. Go over to edit. Hit enter.
I did it where it says name.
Okay? Yours might say 0 by 0 right now, or another number. Make sure it says 3 here. So press 3, enter, to get the 3 there, and then 4, enter, to get the 4 there. Next. At this point, you're going to see that it only shows 3 of my rows. Well, the 4th row is if I keep going over. Or column, sorry. It shows only 3 of my columns. If I go over 1 more, it goes over to the last column. Here's the last column. And then I can go back over, and then go back to the first column. So I want to input exactly what I had on my problem a second ago. So -5. Negative is down here, people. If you use this negative, you're going to get an error. -5. The next one was sine, or do you want to read it to me, Larry? 7 sine 45. Now watch what happens. It puts in a number. Before I do this, hold on. My mode is in radians, see? So I made sure to go back and put it in degrees, because I'm using degrees. Let me go back and do it, because I realized that number didn't make sense. Okay, see? Now here, oops. I want, what is it, 7 sine of?
45.
45, thank you. Enter. Look at the difference, guys. In radian, it came out to 5 point something. When I fixed it to degrees, it's a very different number. Next.
-17 sine 60.
-17 sine 60. Next.
1.
1 or 0?
It's 0.
It's 1.
It's 0.
It's
Oh,
0.
it's 0.
You didn't
It is
count that
1.
0. I'm not there.
Oh, I thought-
Next.
I thought-
Because I had a 0.
1.
Go ahead.
Sine 45.
Go ahead.
Negative sine 60. Then it's 0. Then
Good.
it's another 0. Then it's sine 45. Then it's -0.5.
Again. -0.5 came from where? It was negative cosine of 60, which again is -0.5, and then 0. Okay? Now,
Yeah.
here's what we got to remember. Quit out. Everybody, you got to quit out from here. If you don't quit out, it won't work. Because the next command, it will put it into your matrix, which is called an infinite loop. You'll keep trying to do a matrix within the matrix. So here, press second matrix, go back in, go over to math, go down until you get to, very good, Monica, RREF. So keep going down. Mine froze. You gotta be kidding me.
Where's that? I got it. 1.1001.
Okay, mine froze. You're gonna go down until you get to RF. Hit enter on RF.
That's A, right? I thought it was RRE. Which one is it?
Okay, RREF, RREF, RREF.
Second A, right?
So it's B, is the B one. Now, once you get RREF, you go back into your matrix again. Okay, you choose the first one, you hit enter, and you're gonna get, no, all zeros. We'll talk about that on Tuesday. We'll talk about that on Tuesday.
I got 1 and 1.